get started. So, a few announcements I want to make is there's a few things that are going to pop up here that one already did. So this worksheet here under the mystery day, that I made 4 problems related to circular motion stuff for you to do. Those are worth tokens, but they're just practice problems similar to what we've done in class, just to give you practice setting up some of those problems and solving them. This one is the worksheet I'm going to hand out later. But basically, if you solve the numbers on the worksheet, you can just plug your numbers into that space. It has the same number. So it's just, if you want to get those tokens, you can do that. There's 6 Newton problems there that you can do. There's blank worksheets and then the solution. So if you just want to practice working through some more Newtonian chapter 5 problems, you can. And notice that this Friday, we're going to take a test. And so the topics, I wanted to walk through those real quick. So in chapter 4, that was kind of about just the forces in general and Newton's laws. So basically, we should be able to do all those different things that are not italicized and bolded. Those would be where I can write multiple choice questions from. Notice that one of the things bolded in chapter 4 is using the second law with your kinematics information. So that would be like an extended response problem similar to the Superman problem in the train we did, right? So make sure you're familiar with those. Now the free body diagram drawing, that's going to come more into your extended responses. So in the extended response questions, I say you must draw and label a diagram. So if you don't do that, you will lose points. So roughly, you'll have at least 2 of the extended responses you will need to draw a diagram for. All right, in part of that answer. But basically, you should be able to identify action-reaction pairs, use the first law to remember things about inertia. Second law is F equals ma, and the third law is related to, again, to action-reaction pairs, but the forces are equal and opposite. Right? So that was kind of chapter 4. Now, chapter 5 is almost all bold because chapter 5 was mostly about solving different kinds of problems. So a lot of that is related to solving problems. So you should expect to be able to draw and label a force diagram and some forces for some kind of system or problem, right? That's an expectation on this test. You should also, notice on the multiple choice here out of this chapter, it's distinguishing between mass and weight, knowing that difference. Identifying forces on objects because of the third law. Law of gravity, we're going to talk about that today. And understanding the relationship between force, mass, and acceleration, remembering that that's an inverse relationship, right? So there's an inverse relationship between mass and acceleration, and those two are equal to force. And then being able to remember key ideas about static and kinetic friction and how they work on an object, either when it's stationary or when it's moving, right? So some kind of concept related to that. But don't worry, it can also show up in like extended response problems too. It's not one thing. Now today, but we've talked about some of this already, calculating period, frequency, and speed of an object. You should be able to do that for circular motion. You should be able to use the second law for circular motion, like we looked at looking at brakes or tensions in ropes, like, you know, the idea that not brake, but friction forces for going around turns, something like that. Or, you know, tension in a string if it's moving in a circle, or basically finding the apparent weight of an object in circular motion, right? So we kind of looked at 4 different cases of that Friday. So you should be able to do those. You should be able to look at circular orbits of planets and satellites. We're going to talk about that today. Use Newton's law of gravity to calculate gravitational forces. We'll talk about that. Or you could use solve a problem about gravity and orbits. We'll talk about those last 3 things today. And I'll kind of tell you, hey, if this shows up, this is what it's going to look like. All right. Is everyone good with that? And of course, you get an equation sheet as you have on other tests. So I did give you what I thought was, hey, you should have this on your equation sheet. It's at least a starting point. If you want to put more on there, you can. But that's my starting point for the equation sheet. Any questions about that? Then we'll move on to today's topic. One last thing, in learning catalytics, there is something called like test 2 extra questions, and that'll be open till Friday. Those are just some multiple choice questions for you to practice if you want to. All right, on various things. All right, gravity and orbits. So we want to talk about universal gravity and orbits. So the big thing, and this is a big thing. So we have to put this into a little bit of context. So back in Newton's time, there was a lot of things that we would not, in modern science, they wouldn't be part of modern science. And they stem back, going back into like the BC era, they just kind of got ingrained into society as the way things work, and they became unbreakable rules, essentially. And some of these things, it just was like the idea that there's a separation between heaven, like the heavens where the stars were, and down here on the earth. And the rules and the laws that applied up there were different than down here. Things up in the stars, like planets and stuff, they were all perfect spheres. They all had to move in perfect circles. And there's just all these weird things that all the rules and stuff were different everywhere. Like different rules applied differently. And as the story goes, which is not a true story, but it helps illustrate this idea. The idea was that Newton was sitting underneath the apple tree one day, and the apple falls and hits him in the head. And then he realizes the thing that, oh, the same thing that pulls the apple down to the earth, that's the same thing that holds the moon in orbit. And it doesn't sound like such a big thing, but in Newton's time, that is a monumental ground-shifting concept to say the same rules that are here on Earth are the same rules that the heavens work by. And that is a big, big deal. But once Newton makes this connection and comes up with his law of gravity, it rewrites everything. We suddenly have this understanding we never had before of how things work. So that's what we're going to look at. Just know that this is a big shift. The next big shift is until Einstein comes along, and that's another, like we hit Einstein's equations for gravity, and then we have quantum mechanics. Those are the next two shifts, and that's 400 years later, right? So this is a big break from what we've known, and this is the law of universal gravity. And so universal gravity is the following idea, that all mass attracts other mass. So if you have any two chunks of mass, they attract each other. There's an inward force of attraction. And it's really strange to think about, but my red and blue markers, there's a force of attraction between them. Gravity says that they're pulling towards each other. Now the thing that comes out of this is the gravity forces are small between small objects. So I can easily hold them apart without much. Matter of fact, the friction force of the table prevents the markers from moving because the forces are so small. So when you take two small objects, M1 and M2, and you multiply their masses together and divide by the separation distance, you have to multiply it by this constant. And ironically, that constant is called big G. Even though it's 6.67 times 10 to the minus 11. This is a small number, right? It's a very small number, which is why most normal objects don't attract each other. You don't get this force of attraction between them because you need a lot of mass to do that. But this law tells us that all mass attracts other mass. And the big thing that comes out of this is this turns out to be one of the rules in like how stars form and how solar systems form and planets and all things that happen in space. Because in space, there's not a lot of resistive forces. So matter can just start clumping together. And you clump enough matter together and you get big things. So in space, it works out very well to form things. But here we'll talk about different things, but this is the idea. And the other strange thing that comes out of this is mass is only attractive. Mass doesn't have a repulsive part to it. So you may think about this, like how many people have played with a magnet? Okay, some of you. If not, come, I'll give you some magnets. They're really fun. But magnets, you can take two magnets and they'll stick together. And then if you flip the magnets over, they repel each other and you can try pushing them together. Or you can do the fun thing where you just take the magnet and stick one on one side of your hand and one on the other, and they attract each other. And so magnets can be attractive or repulsive. And there's other things too, like electrons and protons. Those can be attracted, like electric charges have different properties to them. They can be attractive or repulsive. Not gravity. Gravity is only attractive. There is no anti-gravity, right? So it's only attractive. It stands unique in that weird fashion. But the other thing that comes out of this is Newton only knows m1, m2 over r squared. He didn't know what big G was. And that isn't found until a little bit later by a guy named Henry Cavendish. Matter of fact, he calculates big G in an experiment. So he takes two big giant things and floats them in mercury, very safe at the time, and he measures the attractive force between two giant objects that are big enough that he can get to the force between them, and he determines big G, and he gets knighted for that. He becomes Lord Cavendish. Because once you know this, it unlocks everything. If you can calculate, suddenly we knew the size of the Earth, the radius of the Earth. We could determine the mass of the sun, the mass of other planets. Like it becomes a big thing. Once we know big G, we can calculate lots of other properties of other things. So this is a big stepping stone for us in terms of our understanding. So let's look at one application of this, okay? So our first application of this will be to think of the following. So normally we have something like the sum of the forces is equal to MA. But now what I'm going to do is I'm going to say, hey, I can think about the force between the Earth and me. So that is now big G, mass of me, mass of the Earth, over the radius of the Earth squared, because I can assume I'm standing on the Earth. But this is just equal to mg, the force that the Earth exerts on me. Right? Is everyone okay with that? So this is going to be g of the Earth for now. But this is just the mass of me, right? So the mass of me just cancels out. And wouldn't you know it, the gravity on Earth, what we call little g, is just big G me over the radius of the Earth squared. So you want to calculate the gravity on Earth, you can just plug in the numbers. Now you know where little g comes from. It's just a sub-result of universal gravity for the gravity of a planet on the surface. So this is at the surface of Earth. But if you go a little bit higher above the surface of the Earth, what happens to little g? The value gets smaller or bigger? This R gets bigger. It gets smaller. That's why in Denver, gravity's a little bit lower than it is here, because Denver's a little bit higher up. This number's a little bit bigger. Little g is a little bit smaller. But we don't have to restrict ourselves to the Earth. You can say in general, the gravity on any planet is big G, mass of whatever planet or object you're on, divided by the radius of that planet squared. So now we can calculate the gravity at the surface of any object. You don't have to be restricted to just the Earth, right? You want to go visit a different planet? That's fine. You can determine the gravity on that planet, so you can figure out what needs to happen to get to that planet and how you'll function on that planet. Is everyone good with this idea? So we should be able to calculate our next rule. I'll just box this. Our next rule is we should be able to calculate the gravity on another planet. Now I do want to come back here for a second, and then we'll do a problem. I think my slides got backwards, and I just didn't drag it together. But when we're looking at this equation tells us the following. that as we increase the masses up here, the force gets larger between them, right? So force grows as we add more mass, the force of attraction gets bigger, okay? But as R gets bigger, the force decreases rapidly because this is not R, it's R squared. This is called an inverse square law. It's our fourth rule that we've seen now. So we saw linear, we saw quadratic. When we saw like t squared, we see the curvature that way. We had the inverse law with F equals ma, mass and acceleration are inversely related. And now we have our another one, R squared, an inverse square law. And nature really, for some odd reason, really likes inverse square laws. A lot of things go under an inverse square law, especially if you take physics 2. You'll see it crop up multiple times in physics 2, inverse square laws. So the idea is that like if R goes to, you double the R, it becomes a fourth. You triple it, it's a ninth. You quadruple it, it's a 16th. So it decreases rapidly on an inverse square law. But oddly enough, the moon is 250,000 miles away, or still holds it in place, right? Because the mass of the Earth and the moon are very large. And so even at that big distance, it still holds it in place. There's still an attractive force there. All right, but just know that gravity, you should be able to do that. If I start telling you, you have these different masses and distances, and then we change them up, you should tell me how the force of attraction changes between those objects. All right, that's how you would see this crop up on an exam. All right, everyone's good with that. You can look way over there on the other side. So let's calculate the gravity on Mars. As we'll see. So we know they tell us that the radius of Mars, our Mars, is equal to 3.38 times 10 to the 6 meters. And then they tell us that the mass of Mars is equal to 6.42 times 10 to the 23 kilograms. And they want to know what G is on Mars. So we're looking for G on Mars. Question mark. So we can just use our equation for G, and the G on Mars is just going to be big G, mass of Mars, divided by the radius of Mars squared. So in this case, it's our 6.67 times 10 to the minus 11 times our 6.42 times 10 to the 23 divided by our 3.38 times 10 to the 6 squared. But notice here, a planet is big enough that this number is at negative 11 and 23 still leaves you with 12, a power of 12 there. And that's enough to start having gravity. Is everyone okay with that? One other thing to note, these distances for the radius, they always have to go in meters. Even though like the problems will give you kilometers in a lot of them, that's how planetary data is given, it has to go in meters. So that's 3.75 meters per second squared. So gravity on Mars is a little bit lower than it is on the Earth, huh? So that's because Mars is smaller than the Earth by a fact, so Earth is about 6 times 10 to the 24. Even though the radius is bigger, it's 6.4 times 10 to the 6. That additional mass drops it quite a bit. So this is gravity on Mars. It makes landing on Mars difficult because it has a thin atmosphere, but not enough for aerobraking. So you have to have rocket thrusters and other things to slow you down. All right, so let's take a look at orbits. All right, let's talk about orbits for a minute. So I want you guys to remember something. You remember chapter 3? And in chapter 3, we talked about horizontal launching. Does that sound familiar? And when we launch something horizontally, what was the initial in the Y? It was what?
Same as the X.
If I launch something horizontally, how fast is it moving in the Y? Initially. Y is it's 0, right? So VIY when you launch something is 0. So if we're thinking about launching something, here's me. I'm going to launch a ball horizontally. If I launch something horizontally, VIY is 0, but I want to figure out how much time I have. Now I tell you what it is, but let's look and remember Y. We know that delta Y is VIYT plus 1/2 AYT squared. And delta Y, then we're giving up 5 meters. So this is -5 is equal to 0, because initially we're not moving in the Y. And then this is -1/2 9.8 T fall squared. So I get 10 divided by negative 9.8. My time to fall is the square root of 10 over 9.8. So I multiply both sides by 2, divide 9.8. Now you don't have to pull out your calculator to get this time. What's 10 divided by 10? 1. What's the square root of 1? 1. So this is about 1 second. Right? Probably it's like 1.02 or 1.01, but it's about 1 second. So when I throw something and I'm standing on a 5-meter hill and I throw it out horizontally, I have how much time? 1 second. So if I throw it really slow, the ball lands close to me. And if I throw it a little bit fast, I don't want to go down. If I throw it a little bit faster, it will land a little farther away from me. Because no matter how fast I throw it, how much time do I have? 1 second. Right? No matter how, it just lands farther away if I throw it. Right? But here's the kicker. If I throw it fast enough, if I can throw it at 8,000 meters per second, the Earth is curved. And so 1 second later, I travel 8,000 meters and I'm at a height of 5 meters. So how much time do I have to fall now? I'm 5 meters above the Earth. I have 1 second. So how far am I going to travel in my next second? If I'm moving at 8,000 meters per second. 8,000 meters. And then after I've traveled 8,000 meters, how far above the ground am I? 5 meters. And how much time do I have? 1 second. And how far am I going to travel? And I'll be, again, how high above the ground? And I have how much time? So if I can move at 8,000 meters per second, I will constantly go around the Earth. Because I will be matching the curvature of the Earth. And I will never reach the Earth. All right? That is called an orbit. When you're constantly in a state of free fall around the Earth. That is how you orbit. You just have to be moving fast enough. Newton realizes this. They just thought there's nothing that can ever move that fast. Right? So Newton does calculate the speed needed to orbit the Earth. But he said, what can move this fast? Nothing can move this. So they just thought of it as a ridiculous, it was an exercise of mathematics, nothing more. Alright, matter of fact, you can also calculate the speed to escape the Earth, but that number is at 11,200 meters per second. So it's such a big number, there's nothing that can move that fast. It's an exercise in futility, right? Plus, and near the surface of the Earth, what problem do you have? If you're moving at 8,000 meters per second, what's slowing you down? Drag force, because you put 8,000 squared into the drag force equation, you will slow down very rapidly, right? So nothing is going to do this. Now, he thought about this in terms of cannonballs, which is the fastest thing they had at the time. And there was there's no way you can launch a cannonball at 8,000 meters per second, right? So it's a very challenging thing, but they thought about it. And this is the idea of orbits. When you're going around the Earth, you need a force to actually hold you to the Earth. That's gravity. Gravity is constantly pulling you down to the Earth. So if we think about it this way, if this is my velocity vector, here's the gravity vector. All the gravity vector does is hold you to the circle. Right? So gravity is holding you to the circle because you're always at a right angle to gravity. Is everyone good with that? So the centripetal force is what's going to hold you to the circle. Gravity will hold you in the orbit. It also can cause other problems, but the initial part is it holds you to the orbit. Is everyone okay with that? I'm going to erase this. So we're going to look at orbits. And the idea is that you move fast enough, you can do that. Now we're going to derive this equation, but I have it up here as a start. So the idea is the following. You have we're just going to say the radius of some planet. And you want to orbit above that planet at some distance h above the surface. So the radius of our orbit is here. This is r of the orbit, right? So we're going to be some distance above the surface, that's h, and you measure from the center of the object, from the planet, such that the r of your orbit this is equal to the height, this is above the surface, plus the radius of that planet. So when you orbit, you measure from the center of the planet out to the distance you are, and that's the r that we're going to put into our equations. Now, we said that if you're going to orbit, you have to sum your forces in the radial direction, and you get mv squared over r. And the force we put in here is big G, mass of the object in orbit, so here's our little object, divided by the mass of the planet, or multiplied by the mass of the planet, divided by the radius of the orbit squared. And that's equal to the mass of the object divided by the v squared of the orbit over r of the orbit. So we notice again, in circular motion, the object moving in the circle doesn't matter. The mass of that object doesn't matter. And so what we see then is this r cancels one of these r's, and we see that v squared for our orbit is just big G m of the planet divided by r of the orbit. And then you can take the square root. And so there's several things we can take away from this. The first is, as r of the orbit gets bigger, v gets smaller. All right, so you notice that as r gets bigger, the v needed gets smaller, which is why when you're out in space and you're orbiting the Earth, the speed you need isn't 8,000 meters per second. All right, it's a little bit lower, much easier, 7,000 something, much easier. The second part is that this v for this orbit, if you slow down and you don't maintain that speed, you spiral inwards, because it means you're not moving fast enough to maintain the orbit, you'll spiral inwards. They do that a lot of times to decommission old space junk, if they can. Then they have a spot in the Pacific Ocean, all these things landing. Yeah, you can look it up. There's a place in the Pacific Ocean, they crash all these things too. But the idea is that you need that speed. Now, if you're going faster than that required speed, you're drifting away. And you'll change your orbit up to some other distance r above the surface until your speed locks you in. But if you go too fast, you will drift away. So that's important to the v. It's a certain v that we are going to maintain for our orbit. Is everybody okay with that? So this equation goes up over here because it's another equation we should have. So we should either be able to calculate v of an orbit, should be able to calculate the v of an orbit, or notice how the orbital speed changes if we change m or r. You should be able to do that. One last thing about this. This isn't restricted just to Earth. If we want to put an orbiter around any other object, we know what speed that orbiter has to be inserted at, right? We've put probes around comets, asteroids, moons, and other planets because we know what speeds and where they need to be to make that orbit correct. All right. So this is a powerful equation. These equations, they use them in different forms, but these are still the basis of what they use to put things in orbit in other places, more or less. Now you have to do it on different shaped orbits, but it's still the same idea. Is everyone good with this? That's how we know how to orbit things. Now, the next one is we want to calculate a period, or the time it takes to orbit. And this one we're gonna just start with an old favorite from the beginning of chapter 6. Does anyone know does anyone remember? Does anyone remember the relationship between velocity and period? It's one of the first equations I gave you in chapter 6. You're getting slowly there. So I'm going to start you off. V equals. And so what shape or what distance are we running when we're moving in circles? We're running, what's that called when you go around? Circumference. What's the equation for circumference of a circle? 2 pi r. And what goes down here, because it's distance over period. So the velocity is 2 pi r over period. Now what we can do is we're going to square everything here. So we're going to say v squared is 4 pi squared r squared over t squared. And the reason we do this is so we can use the v squared version up there. And we can say big G, mass of a planet, over r of the orbit is equal to 4 pi squared r of the orbit squared over t squared. Now we can solve for t, and t squared is 4 pi squared r cubed over big G mass of the planet. That's still the word. Now I prefer this form because I always get nervous of having to plug 3 halves into my calculator. That's the finalized form, but I prefer this period squared form. Also, this is a law. Does anyone know whose law that is? To get extra credits. It's not Newton. Somebody else before Newton. Somebody else notices this relationship. They just don't have all the constants.
Galileo.
Close.
Aristotle.
Aristotle's way too early for this. Aristotle's the guy that messed us all up. But this is Kepler. Kepler has 3 laws of planetary motion. This is the 3rd law, that the orbital period goes with the radius. So he's like trying to figure things out, and he just starts plotting things. And eventually he says he took the orbital period squared and plotted against the radius cubed for the known planets we had at the time, and they all fall perfectly on a straight line. He plots period squared to r cubed. Now he doesn't know, he gets a slope, but he doesn't know that it's 4 pi squared big G over mass of the sun. He doesn't know that. This is Newton, not Galileo. Newton figures that constant out for us. But he's the one, Kepler's the one that makes that connection between us. He's also the one that realizes planets orbit in ellipses, and there's differences in the speed of the planet as it orbits as well. The speed is variable. But this is that law. All right. So this is also very critical, it turns out, because if you can measure the period of an orbit, you can determine the mass of the planet it's orbiting, or the mass of the star that it's orbiting. Right? Once you know the period, so if I can measure the period of a moon around Jupiter, and I can estimate the distance, I can tell you the mass of Jupiter. I know the period of the Earth. I know roughly the radius that the Earth orbits at. I can tell you the mass of the sun. Anything that once you know 2, you can determine the mass of the object that it's orbiting. And this is actually the first time we can measure the mass of the Earth, right, accurately. So we can also get to the radius of we can get to suddenly all these different things. We unlocked the solar system with these couple of equations. And these are the same ones that they use to look at exoplanets and stars, other stars, and calculate properties of other things. It all starts with these types of equations here. All right. So these became very powerful tools, especially to astronomy. So these are very important equations to science. All right. So we now have our last equation, that the period squared is 4 pi squared r cubed over big G m of whatever you're orbiting, be it a planet or whatever. Planet, comet, asteroid, another sun, whatever it may be. You orbit whatever you like. Right? Is everyone good with that? So you should know these 4 equations. I'll have to bring the camera back over. So let's calculate the orbital period of the lunar command module. So we're going to shift these over here. So they tell us that the command module is going to orbit 110 kilometers above the surface. And they tell us that the radius of the moon, right? So we're orbiting, we draw a picture, the radius of the moon is 1740 kilometers. So we know the height above the surface we're orbiting, and we know the radius of the moon. Now they do tell us the mass of the moon. We'll write that right here. The mass is equal to 7.3 times 10 to the 22 kilograms. And so if we want to orbit the moon at that distance, we know that our orbit is going to be 110 plus the 1740, which means we're orbiting at 1850 kilometers. Is everyone okay with that? So if we want to get our period, we know that period squared is 4 pi squared. Now we can't put in kilometers. We need to put this in meters. And we know that it's 10 to the 3 when we move it from kilometers to meters. And then we cube that. And then that's over our 6.67 times 10 to the minus 11. And then it's times the 7.3 times 10 to the 22. Now, I will let you know that these problems, you have to be very careful with how you put things into your calculator. Because you make a mistake putting something in or miss a parenthesis or something, and you'll get the number all wrong. But just as long as you're careful with how you put things in, then you should be okay. Like something you 7,000.
7,164.2.
64. Yes, orbits take time. Like the International Space Station takes 90 minutes, right? So these numbers are bigger. I mean, things take time to orbit things, right? So this is like, what 100 and some minutes. It's like an hour, a little over an hour, which isn't uncommon. All right, is everyone okay with these ideas, these 4 new equations? So what we're going to do is I'm going to pass out a worksheet. And like I said, you can work out the numbers on the sheet. And for our friends at home, they have these 4 equations to copy. But you can work out these numbers, and I'm going to open up the place on Canvas that you can put the numbers in. But I have one last thing to show you while we pass out. I'll just collect a activist. And everyone was able to get into learning catalytics and answer the question. All right, so here's my funny moment related to orbits. Anybody who's ever watched Family. If you want, you can always calculate Peter's mass just by looking at the timing the objects, how long they take to go around, and then using a standard sofa as roughly a distance of the size of Peter to get his radius. And then you do that, and he turns out to be, he's like, to do that gag, he'd have to have the mass of like a neutron star. kind of thing. So, but it's funny to think about that they actually threw that into the cartoon. Yeah, I won't. Alright, so the idea for the fishing line, on our way out. The fishing line, they tell us that the mass of the fish, the weight of the fish, I should say, is 5 newtons. Now, they tell us when there's a tension in the fishing line. And they tell us that there's an upwards acceleration of 1 meter per second squared. So we know tension minus weight is ma, or the tension is the weight plus ma. So we know because it's accelerating upwards, that the tension has to be larger than 5. Alright, that's all I have. That those solutions to that sheet, you can post those online, and it should be for the math. That's in kilograms, not in kilometers. I know it says kilometers on the mass of the planet, the Earth, but it should be in kilograms, not kilometers. Alright, I'll either see you Tuesday or Wednesday. Thanks.